storage solutions are driving a transformative shift in the energy industry, moving away from the traditional fossil fuels towards the cleaner, renewable alternatives. Among these, biofuels and hydrogen hold immense potential as sustainable fuel resources. Ensuring fuel purity is crucial as even trace contaminations can significantly impact performance and efficiency. Thermo Fisher Scientific's chromatography and mass spectrometry solutions combined with digital science solutions offer state-of-the-art analyzer and advanced testing methods adhering to ASTM standards for precise impurity analysis in hydrogen biofuels and energy storage technologies, helping optimize performance and power the clean energy revolt. With those words, may I request the product head, Trace Elemental Analysis and Inorganic Mass Spectrometry, Thermo Fisher Scientific South Asia, Dr. Piyush Devkar, to kindly take over. This is a masterclass session over the advancing renewable energy through innovative testing solutions. Over to you, sir.
Good afternoon, everyone. So, for today's session or the masterclass, I'll be talking about advancing renewable energy through innovative testing solutions. But before I dive into the topic, in general, I'll cover a quick overview of what Thermo Fisher Scientific is, the analysis of lithium-ion batteries, and then extending the same principles to other technologies, renewable energy technologies as well. We'll talk about hydrogen purity analyzer, like how the analytical instruments can help in the hydrogen purity analysis, impurity profiling in solar cells, some of the software solutions dedicated for this particular industry, and then if there are any Q&As, we can take that as well. Before I begin, we can, just a quick introduction about my organization. So Thermo Fisher Scientific, it is a US-based company. It is in Fortune 500 with more than 100,000 colleagues globally and around 6,000 R&D scientists. One of the key things which Thermo Fisher does differently is investing heavily in R&D, and we invest around $1.4 billion annually in our R&D. We have a revenue of more than 40 billion. We take pride in our mission, which is to enable our customers to make the world healthier, cleaner, and safer. And with that mission statement, all of the next few talks, we will be, or next few slides, we'll be talking about how we can make the place a healthier, cleaner, and safer. Being a very broad organization and multiple divisions, I belong to a division called as chromatography and mass spectrometry. So the instruments which I'll be talking about would be basically towards atomic level analysis and molecular level analysis. And since these are all laboratory equipments with where the samples will be pre-treated before they are analyzed, the basic principle, even though I'll be covering it in only one particular vertical, it can be extended to another verticals as well. So let's start with analysis of lithium-ion batteries. I mean, we are all aware of the energy storage challenges and what lithium-ion battery holds as the future of the energy storage. So when we are talking of mainly analysis or manufacturing of battery, we divide it into cathode, anode, and electrolyte, and then we check the purity of each of these materials. The performance of the batteries, when batteries were directly imported in India, there were few battery fires which were associated. So we studied that, and we are trying to now design the batteries which will be safer in Indian environmental conditions. So when we do that, we have to go all the way up to molecular level or atomic level and understand what exactly is happening there. One of the perspective, other than calcination and growth profiles and physical properties, which Thermo Fisher also has, the division which I'm dealing with, we talk of atomic and molecular level analysis, which are used in QC failures, detecting impurity profiling. We check whatever materials are used, may it be the cathode, the anode, the electrolyte solutions. If we are using separator films, if there is any leaching happening from the separator films, we can study that as well, and so forth. So if I divide the battery into cathode, anode, and electrolytes, we can determine the capacity and voltage by analyzing what type of raw material we are using, LiCO2, FePO4, and so on. For anode, we can analyze the graphite powder for its purity as well as impurity profiling. And same is the case for electrolytes, which you will be using. So the three major techniques which are used in battery analysis would be, from now instrument perspective, would be elemental analyzer. So instruments which will give us information about elements of the periodic table. So that includes purity as well as impurity profiling. Gas chromatography, so that will give us the information about electrolytes and failure analysis as well, because when we talk of battery failures, most of the times it's electrolyte decomposing and forming more volatile molecules, which causes the battery to swell. So we not only can measure the electrolyte itself, but we can not only measure the electrolyte itself, but we can also measure its decomposition products. And there can be a backward calculation which can be done to analyze what type of reactions might have resulted in those products. And the third one is ion chromatography. So this technique will allow us to determine the concentration of counter ions, so negatively charged ions, in our battery setup. Or for that matter, if I extend this concept to any other type of analysis, may it be, let's say, electrolytes used in hydrogen production, the instruments will remain the same. The sample preparation might change, and the molecules or elements which we are trying to detect at the end of it might change. But the basic setup of the system remains same pretty much across the entire portfolio of different verticals. So now when we talk of elemental analysis, we have a couple of instruments in our portfolio. The workhorse would be a ICP OES, which is inductively coupled plasma optical emission spectroscopy. So this is something, the principle we have used it since our 10th standard chemistry, where we take inorganic salt, we hold it in flame, and then we see colors. So if it's a blue color, we say it's copper. If it's yellow, it's sodium, and so on. So this instrument works on the same principle. Whatever elements we want to quantify, we prepare the sample by dissolving it in acid media and then dilute it to a known concentration or a known volume, and we introduce it in ICP OES. The ICP OES enables us to quantify all the elements of the periodic table except the halogens and atmospheric gases. So we cannot do fluorine, chlorine, bromine, and we cannot do carbon, hydrogen, nitrogen, and oxygen. But other than that, around 65-70 different elements of the periodic table can be easily quantified from as low as parts per billion level, so ppb level, which is 10 raised to minus 9, all the way up to percentage level. So I can do purity as well as impurity, as I'm mentioning. And this is a good solution, especially for raw material analysis or in the production facilities where not a lot of R&D happens, but it is set methods which are checked over and over again. When we talk of R&D, we have an instrument which is around 1,000 times more sensitive. So it will help me determine impurities at absolute level. For ICP OES, when it goes below ppb, I just say it's less than 10 ppb. But with ICP-MS, I can quantify absolutely what is the concentration of different metals, even in ppb level. So whatever ICP OES can do, MS can do. Apart from that, 1,000 times more sensitivity is something which is the added advantage with ICP-MS. Now, whenever we talk of new fields, one of the challenges, do we have to sit and develop methods for everything, that we will be analyzing? And with Thermo Fisher, that's not the case, because all of these general methods now may be analysis of anode or electrolytes or cathode material or others in which, raw material analysis or recycling of electronics. The methods are developed and are available on for open access on Thermo Fisher's website. And the instrument parameters, the sample preparation, the recipe basically is given. So it's a matter of replicating that recipe in your laboratory and continuing with the analysis. So there's nothing which you'll have to do from scratch or do a lot of R&D for this purpose. One of this example of ICP OES, which I was discussing, is the analysis of major and minor elements in lithium-ion batteries. And the analysis is in compliance with YST 798 2012 Chinese standard. So the method is set in this way where it complies with the Chinese standard. And multiple elements are analyzed, the wavelengths which were selected, the concentration, and the detection limits of the instrument. All of this is basically the information which you will get in software the moment the sample analysis is done. Second one is trace elemental impurities. Now here in the electrolytes, so this is again for the elemental content which complies with a separate Chinese standard, which is HGT 4067 2015. And it talks of again different elemental concentration, but this time in the electrolyte solution. ICP-MS analysis for lithium-ion salts for its entire profiling. Now, these type of analysis are generally done in the R&D facilities when the batteries are in development stages or performance optimization is done for these batteries. Going towards elemental analysis, but the organic part, which is carbon, hydrogen, nitrogen, or oxygen, we have a system called as a CHNS analyzer, which is generally used for graphite and carbon and sulfur content in the graphite, which is used in batteries. So we do have an application note for that as well, where the analysis of carbon and sulfur content is done in a LiFe PO4 battery. Now, talking of gas chromatography, this is the instrument which now shifts the focus onto volatile organic molecules, and this will help us determine if there are any changes, decomposition, degradation, or disintegration happening of the electrolyte when it goes through multiple charging and discharging cycles. And it can help us probably then optimize the electrolyte mixture so that these decompositions can be either prolonged or avoided altogether. So the gas chromatography, it allows us to determine molecules, and depending upon the detector which we are using, we can determine concentrations in ppb level, ppm level. We also have HR, like high resolution accurate mass spectrometers, which can be used for identifying unknown products as well. So sometimes if a company is going ahead with a new electrolyte which they have developed, the decomposition products might get difficult to judge. And for those type of products, we also have accurate, high resolution accurate mass spectrometers available. So here are a few of the examples, and again, the methods are readily available on Thermo Fisher's website. So if you are interested, please go ahead and you can download these methods. And finally, the ion chromatography. So whenever we talk of any salts, it will decompose as positively charged ion and then negatively charged ion. So the negatively charged species can be done or characterized using ion chromatography analysis. So here we have phosphorus degradation, manganese degradation products, anode degradation products. So all the degradation products can be identified using the ion chromatography system. So all in all, if I talk of materials and products, we can use different techniques like ICP, OES, or MS in our, raw material testing, in cathode, anode. We can also use ion chromatography for lithium salts and so on. So just a snapshot of where different techniques which we are discussing right now fits. This is about the lithium-ion battery workflow. Moving ahead to the next topic of the day, which is hydrogen purity analyzer. We again have solutions for testing the impurity and purity profiles of hydrogen gas which is generated. And that is now done using an ISO method 14687 and ISO 21087. And the system which we will be discussing now, it is in compliance with both of these methods. So generally for any hydrogen gas, the challenge is that there are different detectors which needs to be used depending on what type of product we are trying to measure. So what Thermo Fisher has done is we have integrated all of these different detectors in a single system where you can introduce sample and then the sample will get divided and analyzed for its different parameters in a single system. So you don't have to do multiple GC analysis just for one particular sample segment, so that dividing the gas, analyzing it, and giving a consolidated report, everything is possible using a single software. So this is the data for ISO 21087. And these are the different type of analysis which we have done, which is non-hydrogen gases, hydrocarbons, methane, oxygen, helium, nitrogen, argon, carbon dioxide, monoxide, sulfur compounds, and so on. And including different detectors. So some of the detectors which are not available with us, we have collaborations with other solution providers, and we can integrate those solutions within our software as well. So the analyzer, basically it includes one sample introduction, and then the system itself will split the gas towards the different detectors, and all of that information can be consolidated through a single software. So to just give you an idea, this is how the system would look like. All of this is a part of the single software solution and contains multiple detectors. So repeat analysis of sample doesn't need to be done. Now, finally, coming to the topic of solar cells and silicon, we have a solution of glow discharge mass spectrometer, which is again a high resolution mass spectrometer, which can be used for determining impurities in solar cell silicon at ppb level. If we talk of analysis of silicon by any other technique where the sample is converted to liquid, the problem is even the impurities will get diluted, and reaching the lower detection limits will not be possible. So this instrument allows you to connect a solar cell wafer in a solid form directly into the system, and a argon plasma will evaporate the sample right from the surface, which goes into the mass spectrometer. So that way you can analyze the direct solid sample without changing it into a liquid form and then back again, doing the calculations back again in the solid form. So in terms of sample preparation, it's quite simple. We grind the silicon sample in shape. It has to be flat on one side, and the dimensions are at least 20 mm and maximum 60 mm diameter. Once we do the grinding, we wash and polish it, and then we wash it again with a deionized water to remove any contaminants. We again wash it out with 10% ultra pure HNO3. Finally, to remove the surface layer, we wash it with 20% ultra pure hydrofluoric acid, then rinsing it with water, and final rinse with isopropanol. And we dry it in inert stream, that is argon. That is the only sample preparation. So basically surface cleaning, ensuring that whatever I will be exposing to the system, it is the actual analysis, the surface does not have any contaminants. And as long as I'm ensuring that, I can characterize pretty much all the elements of the periodic table. So, and as low as parts per billion by directly introducing the solid silicon wafer into solid silicon wafers into a vapor form, and then introducing it into the mass spectrometer. Again, analysis of solar cell silicon, it's an application note which is readily available on our website, and it's again open to download. Now, finally, talking of connecting the dots, when we are analyzing using multiple different techniques, major challenge is to consolidate the data and keeping a track of the entire process. And for that, Thermo Fisher also offers a software solution. So we have multiple different softwares, and integration of those softwares is possible with the help of a sample manager software. So it can fit anywhere in the workflow. We can have systems which are connected to it. We can have audit trail information. We can do data analytics using the software. So specification limits, we can study how the system is performing or how the products are performing with respect to time. Doing all of this while ensuring that we are having data integrity which is in compliance with multiple different parameters made by US FDA, US EPA, and few other data regulatory parameters. So those are some of the solutions from Thermo Fisher Scientific. If you have any questions, I think I had spared 10 minutes for any Q&A. So I'll be happy to answer.